All right, welcome everyone to another deep dive. Today we're tackling something pretty monumental.
Well,
We're
yeah.
going right to the source on
Yeah.
Albert Einstein's,
Right.
on the special theory of relativity. Now, what's so cool about this is Einstein wrote this for a general audience,
Right.
like folks like us
Absolutely.
who want to understand these big ideas without necessarily having to go and get a PhD in physics.
Right.
He's famously quoted as saying, I'll leave elegance to the tailor.
Yeah.
I'm all about making things clear.
That's right.
So he deliberately chose
Fascinating. Yeah.
to prioritize clear explanations over, really complex math.
Yeah.
So that's our mission today, too.
Absolutely.
We're going to unpack these core ideas of special relativity straight from Einstein's own words, and we're going to try to get to those really kind of aha moments.
Without getting bogged down in
the minutiae.
Right. Exactly. So I think to really appreciate the significance, you have to understand just how crucial special relativity is.
Yeah.
For all of modern physics.
Right. It underpins so much.
It's foundational.
Yeah. Okay, so where are we going today? How are we going to tackle this?
Okay.
Well, Einstein kicks things off by looking at geometry and how it relates to the physical world. From there, we're going to explore how classical physics understood space and time. We'll tackle the principle of relativity itself, the very strange idea, a constant speed of light, and then how things like simultaneity and distance become relative. And then finally, we'll touch on those big conclusions of this theory.
Right.
Ready for some really interesting shifts in perspective.
I'm ready. Let's do it.
Let's do it. Okay.
Well, Einstein starts off with this fundamental question about what it actually means for a geometrical idea to have physical meaning. Like, what does it even mean?
Right. To say that a geometrical idea has a physical meaning.
Right. And he uses this great analogy comparing Euclidean geometry to this impressive building from childhood, something you may have admired but didn't quite fully connect with.
Right. So when we're talking about truth in geometry, right? What do we mean when we say something is true?
Okay. Yeah. So Einstein's pointing out that within geometry itself, when we talk about truth, it just means that something logically follows.
Yeah.
From those initial rules, the axioms, it's all about internal consistency.
Oh, okay. So like we can't actually...
The crucial point is that geometry can't actually prove its own starting rules. And even more importantly, those geometrical truths don't automatically tell us anything about real objects out there in the world.
So, like, for example, there's the axiom that only one straight line can pass through 2 points. But you can't really...
You can't prove that within geometry. That's just a foundational rule of that particular system.
But then why do these geometric ideas feel, I don't know, correct? Right. So true. Yeah, so Einstein argues it's because, to a reasonable degree, they do seem to match up with what we observe in nature.
Right.
Plus, we develop these deeply ingrained ways of thinking.
Yeah.
Like seeing a straight edge on something solid and assuming its length never changes.
Okay. So this is where we make this connection to...
This connection to the physical world.
Yeah, the physical world.
Is where it gets really interesting.
Okay.
Einstein says Euclidean geometry steps into the realm of physics the moment we add this idea that if you have 2 points on a practically rigid object, the distance between those points always stays the same, no matter how you move that object around.
Right. So suddenly it's not just theoretical anymore.
Exactly. It's making a statement about how solid things behave in space.
Right. It's a claim about reality.
Right. Exactly. And Einstein argues that the truth of these geometric theorems now, in this physical sense, relies on us testing it out in the real world.
Yeah. Putting it to the test. Right. We trust these geometric truths because our experiences seem to confirm them.
Right. Now, it's interesting, though, because
it's fascinating.
Later on, he hints that maybe
we
need to revisit that assumption a little bit later when we're talking about general relativity.
When he delves into general relativity.
Yeah, so even our ideas about
space
might have limits.
That even our most fundamental ideas about space have their limits.
Okay, so now that we've got that groundwork laid, let's talk about coordinate systems.
Okay, how do we actually describe where things are?
Right. How do we pinpoint a location?
Okay, well, at its heart, it comes down to measurement.
Okay.
Einstein explains that. To figure out the distance between 2 points on something solid. We use a standard unit of length, like a ruler, basically.
Yeah, ruler. You count how many.
We see how many times that ruler fits.
Times it fits. Between the two.
Between those 2 points.
And then to actually say where an event or an object is.
To say where an event or object is.
Yeah, you need some kind of reference.
You need something to refer it to, yeah. Solid, stable object.
Yeah, yeah.
He uses the example of in Berlin at Potsdam Square.
Okay.
Right. The ground is our stable object.
Right.
And Potsdam Square is a specific spot on it.
And we do this.
And this basic idea extends even to things that aren't directly on the ground.
Right.
Like think about locating a cloud. We might use a tall pole to get a bearing.
Right.
Or we could use more indirect methods, like photography, understanding how light travels. But the fundamental principle is still about relating the cloud's position.
Yeah, you need that reference.
To a solid reference. In this case, the Earth.
Okay, okay. And this is where...
And this is where the power of numbers comes in.
This power of numbers comes in, yeah.
Instead of just naming places, using coordinates gives us this much more precise and flexible way to describe locations.
Right.
This leads us to the idea of...
Cartesian coordinate system.
Yeah, the X, Y, and Z. Those 3 imaginary walls.
Right.
At right angles to each other.
Right. Those 3 walls.
Attached to a rigid body.
And even though...
What's brilliant is how Einstein breaks this down.
Physically. Build them.
Even if we don't physically build those 3 walls.
Right.
The fundamental physical meaning of any location we describe in physics or astronomy rests on this idea.
Yeah, of relating it to a rigid framework.
Of relating it to a rigid framework using numbers.
Using numbers, yeah.
Coordinates.
Coordinates. Okay, so we've got space. Now let's talk about time.
Okay.
Einstein tackles this seemingly simple statement. He says, mechanics should describe how the position of bodies in space varies with time. And he says, there's a hidden problem.
Yeah, there's a subtle issue there.
In that sentence.
It lies in those words, position and space.
Right. It's kind of circular.
As we just discussed.
Yeah.
So Einstein uses this fantastic thought experiment.
He does. This is a great one. This is one of the best.
To really bring it home.
Yeah. So let's imagine...
Imagine you're on a train.
We're on a train again, moving at a constant speed.
Moving at a constant speed, and you drop a stone out the window.
And I drop a stone out the window. Okay. Now, to someone sitting on the train,
right,
they see that stone fall. Straight down.
Straight down.
But to someone standing still by the tracks...
But to someone standing still by the track...
They see it follow this curved path.
They see it follow a curved path, like a little arc.
Yeah, like a little parabola. So what's the
real path the stone takes?
Real path, that's the question.
Exactly. Einstein's point is, there isn't one absolute path.
Right.
The trajectory is only defined relative to whatever you're using as your point of reference.
Right, so just talking about motion in space doesn't mean much.
Yeah.
Unless you specify.
Unless you specify what you're measuring that motion.
Compared to, what's your reference frame?
Right.
Okay.
And to fully describe this motion.
Yeah. We need more than just.
We can't just look at the path.
The path. We need to know.
We also need to know when the object is.
When the object is.
At each point along that path.
At each point. This introduces.
The need for.
The need to define time.
A way to define time. And we can actually observe and measure.
Right. So how do we do that?
Okay. So the classical approach, as Einstein explained.
Involves imagining identical clocks.
Being held by observers.
Yeah.
In different reference frames, like in our train example.
Right. One person on the train.
One person on the train, another by the tracks.
Another on the track.
Each observer would track.
Yeah.
The stone's position. According to their own viewpoint.
Yeah.
And the time on their own clock.
Right, right. Okay. Now this leads us...
to the concept of...
To Galilean coordinate systems.
Galilean coordinate systems.
Okay. What are these and why were they important?
So important in classical mechanics. Well, Einstein brings in Newton's first law of motion here. The law of inertia.
Okay. An object that isn't.
An object that isn't being acted upon by any forces.
Being acted upon?
Yeah.
By any forces.
Well, either stay still.
Well, stay still.
Or keep moving in a straight line.
Keep moving a straight line at a constant speed.
A constant speed.
Okay.
This law doesn't just describe how things move. It also defines which viewpoints or reference frames are suitable for using the laws of mechanics.
Right. So it uses the example of...
The fixed stars?
Fixed stars, yeah.
From our perspective here on Earth.
From our perspective here on Earth.
They appear to move.
They appear to move.
In giant circles.
In giant circles.
Across the sky every 24 hours.
Across the sky. Every 24 hours.
Which violates the law of inertia.
Which violates the law of inertia. So our Earth-based system...
Isn't
Galilean.
Isn't a Galilean one?
Yeah.
In the strictest sense?
Yeah.
Although, for many everyday purposes, it's a good enough approximation.
That makes it good enough approximation.
Right.
Okay, so a Galilean coordinate system...
Exactly. A Galilean coordinate system is one where that law of inertia holds perfectly.
Holds perfectly. And the crucial thing is...
Yeah, this is important. Because the laws of motion...
That the laws of motion...
Newton formulated them are only valid.
Newton formulated them are only valid when you're observing things from these Galilean coordinate systems.
From these Galilean coordinate systems.
These non-accelerating frames of reference.
Non-accelerating frames of reference. Okay, now this sets the stage.
So this sets the stage.
Principle of relativity.
For the principle of relativity, at least.
The restricted version.
The restricted version.
That Einstein
focuses on here.
Talking about here. So let's go back to our train. Moving at a constant speed.
Okay.
In a straight line. Now, if something is moving in a straight line at a constant speed, as seen
by someone.
By someone on the train.
On the train.
How will it look?
How will it look?
To someone standing on the ground. To someone standing on the ground. Einstein explains that it will also appear to be moving in a straight line. At a constant speed from the ground.
Okay.
Although the actual speed direction of motion will be different.
Yeah. But the key is...
The key is that the nature of the motion.
The nature,
uniform and straight. Remains the same.
Remains the same across different Galilean systems.
Across different Galilean systems.
That are moving uniformly relative.
That are moving uniformly relative to each other.
Okay. And this leads to...
a
formal statement.
The formal statement.
Of the principle.
Of the principle of relativity.
Of relativity. Now, if one system...
we can call it K, is moving uniformly and without rotation...
Relative
to another system, K.
Then
all the laws of nature. Will be the same in K. As they are in K. Okay, it's
a fundamental symmetry. Now, classical mechanics.
Classical mechanics.
Kind of took this for granted.
Einstein points out.
More recent
discoveries
in things like...
In the fields of electricity, magnetism, and light.
We're starting to...
We started to raise questions.
About whether this was true.
About whether this principle held true.
Yeah, for all physical phenomena.
So
this idea of the principle of relativity was becoming...
So the principle of relativity...
A sticking point.
Was becoming a real point of contention.
Yeah, a point of contention. But Einstein presents...
two
really strong arguments. In its favor.
Compelling arguments in its favor.
Yeah. The first
is...
we've had all this success with classical mechanics.
Incredible success.
Classical mechanics.
Right, we can predict.
In accurately predicting the movements.
Of planets.
Of planets and stars. And stars really accurately. So that suggests... that it must contain...
a significant amount of truth.
So the principle of relativity...
Making the principle of relativity...
is likely
valid at least. In the realm of mechanics. Right.
And the second
argument is quite profound.
Is really profound. So...
If the principle of relativity didn't hold...
the principle of relativity didn't hold true...
It would imply... that different Galilean systems...
That these different systems...
aren't truly equivalent.
So it would suggest...
This would suggest...
that there's one.
The existence of a single...
Absolutely at rest system. Some kind of background.
A kind of fundamental background.
Against which all motion...
occurs.
And the laws of nature...
Where the laws of nature...
would have their...
simplest form.
Which would mean... that the Earth's motion...
as
it orbits the sun...
should
have a measurable effect... on physical laws... depending on our orientation. Right, so we should be able to see...
detect...
this directional dependence.
Yeah,
like...
of physical space here on Earth.
Certain things should behave differently, depending on...
Despite many clever experiments.
Yeah, where we are in a locket.
The orbit...
No such effect has ever been.
But despite all of our efforts, we've never...
reliably observed
it. So this lack of...
evidence.
Evidence for...
a preferred... At rest frame.
At rest frame is a strong point for the principle.
It's a strong point for the principle of relativity.
Relativity. Okay. So we have this principle of relativity.
Okay.
Yeah. Now, how do velocities add up?
According to classical mechanics.
It seems like such a...
straightforward idea.
Yeah.
You know?
I'm walking on the train.
Einstein uses the familiar scenario.
This is another good one.
Of someone walking forward.
Yeah.
Inside our moving train.
I'm walking forward inside the moving train.
The train is traveling at speed v.
Train's traveling at speed v.
And the person is walking at speed w in the same direction.
I'm walking at speed w. Okay. Our everyday intuition
tells us
that
their speed relative to the ground is simply the sum of those two.
It's v plus w.
W equals v plus w.
Right.
It just feels obvious.
Yeah, just totally obvious. And yet...
And this seemingly self-evident result is precisely where our classical understanding starts to run into trouble. When we consider
the behavior of light.
Ah, yes, the speed of light. So, Einstein states this elegant law. Yeah, light travels.
Light travels in a vacuum. In straight lines.
Yeah.
At a constant speed c.
Which
is about 300,000 kilometers per second.
300,000 kilometers per second.
And the speed is the same.
For all colors of light.
And doesn't depend on how.
How the source of the light is moving.
Right,
like if it's moving.
As observations of binary stars.
Towards you or away from you.
Have confirmed.
The light is still traveling at that speed. Now,
the idea that this speed might vary depending on the direction.
Yeah, the direction you're measuring. Also seems unlikely based on
understanding
the vacuum.
The vacuum.
Yeah. So we've got this seemingly
unshakable law.
Yeah.
Of a constant speed.
Of light.
In a vacuum.
But this simple law.
When
combined with
the principle
of relativity.
When we combine it.
Guys, see you in another podcast. Don't forget to subscribe to our channel.